As you know, it's traditional here at Harvard that when a member of our own faculty gives a talk, he's not introduced. But let me dispel any illusions you may have. I'm not Woodward. I've decided that it's time the traditions of Harvard were changed slightly, and that maybe this would be a good opportunity to continue the tradition that we have started in this year's organic colloquia of introducing our own members. If I appear nervous, I am. I feel a little like the man who, knowing that he shouldn't have accepted the invitation to a party, went nevertheless, and finds that horrible moment is about to occur when he's got to introduce his mistress to his wife. My standing here all began about a month ago, I guess, when, as always, I was having lunch with John Osborne, whom I introduced about a year ago. And he said, "Well, Dave, you did such a good job on me. Why didn't you try one on Woodward?" And I thought, no, I've had enough temptations this month. My wife has been away. I've had enough. I was persuaded, however, that perhaps I should try my hand at an introduction. I'm regretting every minute of it now. I'm not sure how one can possibly introduce somebody as well known as Professor Woodward. What can I say that you don't know? Very little. I thought I would start out by giving you the facts. One cannot go too badly wrong with the facts. And then, when we have the facts, we see what we can develop from there. Professor Woodward's career began many years ago at MIT. It was quite clear from his original scientific endeavors that here was somebody who was going to go far. I can have the first slide. Been downhill ever since. The next slide lists some of the other papers which you may or may not be familiar with. I don't want to bore you with the details. I'm sure you're as familiar with them as I am. Synthesis of quinine in 44. Oh, an interesting one. The structure of iron bis cyclopentadienyl may not be as familiar to you as it is at least to me. The next slide shows the structure that Professor Woodward, in fact, suggested for ferrocene. It's rather interesting how these things develop historically, and one might actually use the analogy with Auguste Kekulé when he proposed the structure for benzene. Now, I have here in front of me a description of Kekulé's dream, and since he wrote it, I assume it must be true. It isn't, however, the story that I heard. The story I heard was that, in fact, Kekulé had a dream on top of a London bus. London buses are great places. There are many exciting things that can happen in a man's life on the top of a London bus. And I was convinced when I was told the story that, in fact, this was the location for Kekulé's structural thoughts about benzene, but it turns out not. And let me, before we come to ferrocene, just read what Kekulé wrote. When did he write it? 1865. This, remember, was 40 years before the advent of Freud. There I sat and wrote my Lehrbuch, but did not proceed well. My mind was elsewhere. I turned the chair to the fireplace and fell half asleep. Again the atoms gamboled before my eyes. Smaller groups this time kept modestly to the background. My mind's eye, trained by repeated visions of a smaller kind, now distinguished larger formations of various shapes. Long rows, in many ways more densely joined, everything in movement, winding and turning like snakes. And look, what was that? One snake grabbed its own tail. That's where Freud comes in. And mockingly the shape whirled before my eyes. As if struck by lightning, I awoke. This time, I again spent the rest of the night to work out the consequences of which were, of course, the structure which we now accept for benzene. I'd like to sit back and think for a moment. If Kekulé was thinking about snakes biting their tails when he postulated the structure for benzene, what do you think Professor Woodward was thinking about when he had this sandwich structure in mind? Let's have the next slide. Well, we go through syntheses of terpenes, steroids, chlorophyll, tetracyclines, structural elucidation of tetrodotoxin, cephalosporin, orbital symmetry, and as you know tonight, we're going to hear about the total synthesis of B12. It's said, however, that you can judge a man by the company he keeps, and I asked Miss Dyer, I think early this week actually, if she could provide me with a list of the collaborators whom have worked with Professor Woodward. It's a very long one, over 300 names, and as much as I would like to outline them all in detail, and I trust those that I've left out won't feel particularly unhappy if they're sitting in the audience, I decided to simply go through this list and pick every fifth one and just let you see what sort of names one came up with. Have the next slide. You can imagine what the other 250 look like. It's inevitable, of course, in making a list in this random fashion that you're bound to miss one or two of the more important collaborators. I have those on the next slide. I trust that many of you were here for the titular lecture which Professor Aragoni gave some few weeks ago. You may recall at that time that the introduction was in fact given by tonight's speaker. And much of the introduction concerned itself with a horoscope that Professor Aragoni had prepared for him. And I understand that Professor Woodward took some delight in discussing this in great detail. You may remember that the young lady in question, who had prepared this horoscope, suggested that Dr. Woodward himself might like a horoscope prepared. The unfortunate thing about having a horoscope prepared is that you need to know exactly when you were born. It's no good knowing the day or the year or even the week, let alone the hour. You need the minute. And Woodward's suggestion, I guess, to this young lady was that she should simply prepare a horoscope for each minute of the day, and we could then find out which particular minute he was born in. Well, I've never quite had the financial resources to carry out my research the way Professor Woodward has, and I thought that if we were going to do anything about this, we would have to go about it in a more systematic fashion. Well, the course I pursued was this. Went to Who's Who, first of all, to make sure he was born. Appears he was. He was born in Boston. Now, that has some advantages in this country. Boston's an old city, long traditions, keeps records. So I went to the State House to see what they knew about our speaker. And they confirmed his date of birth, but that's all they had. That really doesn't help us. Everybody knows what that date is. But they had one little bit of information which I thought might possibly help, and that is that he was born in the Boston Lying-In Hospital, which, as you know, is one of our more renowned hospitals in the area. And I phoned the hospital up and asked them if they would keep these sort of records. They said, oh, sure, we have records going back to 1620. Who do you want? So they said, just send us a letter and a $2 search fee and we'll see what we can do. And what they did is shown on the next slide, I hope. Yeah, that's the letter. I've typed underneath it the information in case you can't read the writing. In regard to your request, the exact time of Professor Woodward's birth was at 3:39 a.m. This is authentic. This is no... It's a very interesting time, actually, 3:30. It obviously set an example to him, because it's my understanding that, in fact, Professor Woodward only sleeps about 3 hours a day anyhow, goes to bed at 1 and gets up at 3:30. I guess he started that way and just couldn't change his habits. But anyhow, with this information at hand, knowing exactly where he was born, room 21 in the Boston Lying-In Hospital, and knowing exactly when he was born, I transmitted this information to Zurich, to Professor Aragoni, who is sitting in the audience today, and he flew in today with a very interesting document. And since the only thing I have to lose is my job and my friends and my reputation, I thought I might read some of it to you. Now, as I say, I only saw this horoscope 2 or 3 hours ago, so if I'm a little slow in translating some of the rather unusual symbols, I trust you'll bear with me. The next slide, in fact, shows the horoscope that was prepared. Now, this probably means more to you than it does to me. Let me see what my crib says. Okay, it seems that this line here, labeled AC, is the ascendant line, and it's this line which tells you very much about all the social behavior and one's personal life. Whereas this MC line, essentially orthogonal, is the line which details and outlines one's professional career. Your favorite color is red. The only disadvantage in lecturing at one's own institution is that you don't get an honorarium. However, Professor Aragoni assures me that the young lady who prepared this horoscope is anxious to meet Professor Woodward once again. And although we can't provide you with an honorarium, we might at least provide you with an opportunity. You'll appreciate that in a document as delicate and sensitive as this, that I'm going to have to not only read between the lines, but leave some of the lines out. But if you'd like to come by my office tomorrow and get some more of the details, I guess I can let you in on some of the secrets. Let me be absolutely honest about this. This is a true horoscope we've had prepared. The young lady who prepared the horoscope knew nothing about the individual for whom it was prepared other than when and where he was born. I must say, until this time, I believed as much in horoscopes as I do in half the papers I read in JACS recently, but it seems that the way you work out one of these things, once you know when the man is born, is you see what particular planets and heavenly bodies come into conjunction for any particular aspect of the man's life. And The woman who prepared this horoscope said that it really is a unique horoscope, the most unusual individual about whom it's written. It appears that one can divide many of these subjects we're going to discuss into various subsections. The first one is fire, and it says that in this heading fire, the Sun and Mars and Venus all in conjunction, and that the individual must be highly dedicated, forceful, energetic, and determined. The moon dominates water, a man of great sentiment. In Earth, it's Mercury that's in the ascendants, a good practical sense. Under air, it appears everything is missing. Conclusion is that the man is not diplomatic, and he impresses others with his own views and viewpoints. Now remember that we really did not give any other additional information. Clearly this man should be a scientist. More than that, Pluto influences his personality, and he should be a chemist. Now there's a challenge for you. Apparently once we've gone through the air, earth, sun and the moon, whatever it is, we then have these various houses, each of which covers a particular aspect of the individual's personality. The first house deals with the man's personality. Very sensitive, sentimental, and as a result of his dynamic personality, he's quite attractive to the opposite sex. You mean you don't believe it either? Second house has to deal with money and possessions. The young lady would estimate that the man must be very rich. I'd almost say filthy rich. And his money comes from two principal sources. One is his own profession, and the other is a unique gift for taking advantage of a situation and jumping in at just the right time. It also outlines in some detail here where his money goes, but I think that's one of those sections I'm going to keep closed until later. The third house deals with the heading that says small intellectual matters, items related to his professional activities and such like. It says no special hobbies were noted, but the man is an exceedingly good driver. Probably true. Have you seen Professor Woodward's new car? It's a 4.5-litre super deluxe Mercedes-Benz. It has everything you could need in a car: air conditioning, stereo, speakers, back seat that pulls out to a bed. It even has a console that plugs directly into E.J. Corey's synthetic computer. Let's go past the fourth house. It's not especially exciting at the moment. The fifth house deals with love and sex. I think there you and I, Bob, are going to have a quiet talk after the lecture. House 6 deals with work, health, illness. It says that the man about whom this horoscope is written has a strong attraction to nicotine, liquor, and drugs of all kinds. However, the man has such a strong character that none of these above mentioned will affect his health in any adverse way. I think I'd better miss that one as well. In the 10th house, which deals with his professional life, it says the man will have an excellent reputation in his chosen profession, that he will fulfill all the professional goals that he sets himself, and that probably, and this is an interesting statement, probably this career began when he was about 22. It's off a little, but not all our careers start at 22. And I thought I might just read you some bibliographic information concerning Professor Woodward. This is taken from the book The Importance of Anti-Bonding Orbitals, and it's chapter 5, which is headed The Hofmann-Woodward Wars. I rather wish in a way that I was introducing Hofmann. You may have heard some time ago when Hofmann was being introduced by Osterhoff, that Osterhoff stood up and said, there have been in the history of organic chemistry a number of very eminent Hofmanns. The one associated with the elimination and the rearrangement and the degradation. He said the most famous Hofmann of them all is the one whose first name is Woodward. Anyhow, this bibliographical information says Robert Woodward was born in 1917 in Boston, Massachusetts. He flunked out of Massachusetts Institute of Technology as an organic chemistry student in his sophomore year, was given a second chance and received his BSc from that institution in 19, and by the age of 20, he had received his PhD, and has ever since been at Harvard. I think I'll leave the remainder of this horoscope until the party afterwards, and just detail some of the things that I have learned while I've been here. I guess I came here towards the end of 1965 to spend a postdoctoral year with Woodward, and he introduced me into a number of new and delightful concepts: the 14-hour day, 7-day week, and one for which I shall be ever thankful, and that is the daiquiri. The daiquiri is a sheer delight, and there's only one place I've found in Boston where you can get a really good daiquiri, and that's the Faculty Club. And there's only one man at the Faculty Club that can make a really good daiquiri, and that's Denny. We're ready, Denny. Go to the front. Just hit it. I'll get it out. I'll get it out.
You got it?
Yeah.
That'll do it.
I guess we really don't need this, so perhaps I'll have some more. The daiquiri is a very unpretentious drink. It's basically rum with a bit of sugar and lime. Just the sugar in case you need it. While Danny's making our daiquiris, I'd just like to take a few moments. Professor Woodward's graduate students and postdoctoral fellows asked me, they said, for 3 years we've been trying to get hold of him. Do you think tonight you might possibly be able to give him this present? So. They also insisted you should open it now. Now. Yeah, take your time.
document here. A document which states, presented 27/11/1972 to Professor R.B. Woodward on the occasion of the presentation at Harvard of the total synthesis of vitamin B12. And it is signed by all of the members of my research group. And it is a very lovely object. Thank you.
How's it going, Danny? No, you just carry on making it. Just... Professor Woodward's mother was a Scot. I guess one can never quite escape one's droit de seigneur. You really should. I was just making sure that it was up to the usual standard. Why don't you take one to Professor Woodward, okay? Professor Woodward's mother was a Scot, and I don't want this to sound a gauche cliché, but for many years, the Scottish poet Robert Burns, whom I assume must have been a favorite of Mrs. Woodward, has long been a favorite of mine. And there's one particular poem of Robert Burns that has long attracted me. It's called The Dean of Faculty. It's a new ballad, it says, and it's supposed to be sung to the tune The Dragon of Wantley. Well, my social attributes don't go to singing, especially when I don't know the tune. But I thought I might possibly just read two verses. It's showing the balances and the counterbalances that one might anticipate in a university. It involves two principal characters, Harlaw and Langside, and somewhere there comes in beauteous, hapless Mary. I'm not sure where she fits in, but I guess this is just the old triangle. It's part of the way things go. And this poem is outlining just the way one has to get involved in the infighting in a university if you want to survive. And we have the first verse. Dire was the hate at old Harlaw that Scot to Scot did carry, and dire the discord Langside saw for beauteous, hapless Mary. But Scot with Scot ne'er met so hot, or more in fury seen, sir, than twixt Hal and Bob for the famous job. Who should be faculty's dean, sir? This Hal for genius, wit, and lore amongst the first was numbered, but pious Bob, midst learning store, commandment the 10th remembered. Yet simple Bob the victory got and won his heart's desire, which shows that heaven can boil the pot, though the devil piss in the fire. We're approaching that time in the evening when the real entertainment begins. Are you almost finished?
Almost.
Okay. Do you still need some sugar?
No, I don't.
And there's always a problem when one is introducing a man. And the problem is that, it may be that people in the audience really don't know whom I'm talking about. There's, of course, a simple way of overcoming that. It's to show you a picture of the man. So the next slide. I think you should take the lights out and focus it. That's better, that's better. Now, lest you be misled again, the man on the left is Prelog, not Woodward. This is Woodward here. Rather than let your imaginations run riot, I'll show you, in fact, what he's really doing. For the last slide.
Take care of us.
Okay, good.
Well done.
Well, I think it's time for the real evening's business. The lecture this evening is entitled The Total Synthesis of Vitamin B12, Professor Woodward.
Thank you, David, for that very fulsome introduction, and for having been the moving factor in making it possible for me at long last to speak here at Harvard. Now, I should like to say first that the acoustical properties of this room are notoriously bad, and consequently, should I become so absorbed in what I am discussing that my voice falls to the point that you can't hear, I strongly urge you to shout louder. I shall be not in the least offended if you do that, because I do tend to get interested in what I'm talking about, and my voice falls as I become more and more interested. So please don't hesitate to make it known if you can't hear. Now, I'm glad that David has set a relatively leisurely pace for this evening's proceedings. Some weeks ago, I was in London, and I learned that there was being shown there the entire 26 hours of the Forsyte Saga series, right in consecutive way. That is, people went to a theater and they stayed there for 26 hours while the whole television series, which I'm sure many of you have seen, was played through. I saw a number of them interviewed on television, and they said that they stayed awake throughout the whole thing. Now, presented with an opportunity to speak about the total synthesis of vitamin B12, one is presented at the same time with something of a problem. The investigation which has culminated in the synthesis of vitamin B12 is a very long one, very formidable one. It has led to the establishment of a straight path from carbon, hydrogen, nitrogen, oxygen, and cobalt to vitamin B12. It has led to many bypaths and offshoots, and indeed, were the whole story to be told, the 26-hour foresight saga would more nearly resemble one of those delightful Japanese verses, a haiku, I think, with a few syllables, than the synthesis of vitamin B12. That'd be a lot more complicated and take longer. And so one has to make a choice if we're to get away from here. I was going to say at a reasonable time. You're not going to get away at a reasonable time, but let's say in a relatively short time. Now, I should also, at the outset, like to say and emphasize that the work which I shall describe is a joint effort carried out under what might loosely be called the leadership of myself here in Cambridge and Professor Albert Eschenmoser in Zurich. And we worked, the two groups in Cambridge and Zurich, worked very, very closely together. I don't think I know of any occasion of such close collaboration in which even samples were sent back and forth, reactions were started in one city and finished in the other. It was a very, very close, fruitful, cordial, indeed extremely pleasant collaboration. And it's a very great privilege for me tonight here to be able to be the spokesman for both of these groups, the group in Zurich associated with Professor Eschenmoser and the group here in Cambridge loosely associated with myself. Now, let us first, let's have the first slide. And we need some focusing. That's pretty good, Olin. A bit better. And perhaps a bit less light. How about that? Can almost everyone see it? There's a substantial number that can't. Would they shout? Either you can or you don't like to shout. All right, now there is in all its magnificence the structure of vitamin B12. Lovely structure, established in the 1950s, essentially entirely through the beautiful X-ray crystallographic work of Dorothy Hodgkin at Oxford. Speaking generally, it is certainly the most complicated of the non-macromolecular natural products. You will see that it has this somewhat unusual macrocyclic system with a cobalt atom embedded in the middle of it, 4 5-membered heterocyclic rings forming that one large macrocyclic ring. There's an interesting and, until vitamin B12 was discovered, unique conjugated system running from one of the nitrogen atoms around this internal 16-membered ring to the other nitrogen atom. You will discern in this structure certain similarities to other very important natural substances. Heme, the active portion or inactive portion of the blood pigment, is a porphyrin which has a somewhat similar macrocyclic structure with 4 5-membered nitrogen-containing rings. In that case, rather than rings A and D here, being joined by a single bond, they're joined by one carbon atom. There's a bridging carbon atom just as there is at the other three sites in this structure. And then there's chlorophyll, which is constructed very similarly. Again, one of these macrocyclic rings made up of four five-membered nitrogen-containing rings. And in the case of chlorophyll, the leaf pigment, there is in the center a metal atom, magnesium. In the blood pigment, there was the metal atom, iron. And here in vitamin B12, cobalt. Now, the thing that strikes one immediately about vitamin B12 is the stereochemical situation. In the case of heme, the blood pigment, the entire macrocyclic nucleus is made up of trigonal carbon atoms, and there is no stereochemical problem at all. In the case of chlorophyll, there's a relatively trivial stereochemical problem in that the outer periphery of one of the five-membered rings, corresponding to this position in the vitamin B12 molecule, is reduced so that there are two adjacent chiral centers. But that's a relatively small stereochemical problem. Now contrast that situation, or those situations, with that which obtains here in the case of vitamin B12, where this macrocyclic nucleus contains no less than 9 chiral centers, shown here with stars. Now, obviously, the molecule then, the structure, presented a challenge and an opportunity to the synthetic chemist to test his methods of constructing molecules in a stereochemically oriented way, in a particular stereochemically oriented way, to test the principles that he knew and perhaps to develop new ones. So that much of the interest in this problem devolves from the stereochemical content, its stereochemical content. I will mention only briefly that you can see right away that the chiral centers within the large nucleus are very differently distributed. They can be divided essentially into 3 groups. You see here in ring C there's an isolated one all by itself, quite far away from any of the others. Here in ring B there are 2 adjacent ones, 2 close together, and far removed from the one in ring C, and also far removed from this very different group of 6 contiguous asymmetric atoms. So that you could say at the outset, and we did say at the outset, that we would have to approach the problem in a stereochemical sense in the following way, that we could not see, we would like to have been able to, but we could not see any way in which we could influence asymmetry, let's say, at this point, by asymmetry already present at a point over here, far away from the initial one. So that we had to use here what one should call the principle of absolute asymmetric synthesis. That is, we should have to prepare components representing, let us say, ring C in the optically active form and of the correct in the sense of corresponding to the natural absolute configuration. And likewise, for the ring B portion, we should have to have an optically active building block of some kind in which the relative configurations at the 2 centers was that desired, and in which the absolute configuration of the optically active building block was that desired. And then finally, for this third complicated group of 6 contiguous centers, we should have to have some kind of building block, again optically active, in the right absolute configuration, and of course with the right relative configurations with respect to each other, that is the 6 atoms in this chain. Now, of course, in the vitamin B12 molecule, there are other asymmetric centers. There are 5 others. There's one here, 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 and here. Now, I'm not paying very much attention to those for a reason that you'll see in a moment. You will observe that the periphery of this molecule is adorned by various what you might call acidic chains. There are 4 propionamide chains, one there, one there, one there, and one here. There are 3 acetamide chains, there, there, and there. You'll notice that one of the propionamide chains is different from all the others in that rather than terminating in a simple amino group, there is this rather complicated chain of rather biochemically familiar groupings. This is an isopropanolamine grouping, phosphate, ribose, dimethylbenzimidazole. That whole chain, then, is attached at one of the propionic acid termini and then bonds back to the cobalt. Now, the ribose and the propanolamine portions of that chain, they are well-known substances available readily in optically active form. And so there's no trouble in introducing them. And if we may have the next slide, you will see that the problem of synthesis for Professor Eschenmoser and myself was simplified right at the start by the facts which I've summarized here. The portion in red is that portion that I've just referred to, the isopropanolamine, phosphate, ribose, dimethylbenzimidazole chain attached to this propionamide grouping, itself attached to ring D. Now, that whole chain can be removed, can be taken off to give an acid, this acid. There we just have OH in place of this entire chain. And the substance obtained when that chain is removed is a well-known substance, cobyric acid, or factor 5 sub 1A. It, like vitamin B12 itself, is a natural product. And beyond that, it can be obtained by degradation of vitamin B12. Beyond that, cobyric acid has very readily been reconverted to vitamin B12 by the addition of this isopropanolamine, phosphate, ribose, dimethylbenzimidazole chain. And so our task already at the outset had been simplified to that of the synthesis of cobyric acid. Now may I have the next slide. What I've said hitherto has been introductory, and the lecture proper now begins, and this may seem a peculiar place to begin a lecture on the synthesis of vitamin B12. Why have I started with this slide? Well, one reason is that I like the slide very much. Now, what is it? It is the result, or it summarizes the results of a single crystal, three-dimensional X-ray crystallographic structure determination carried out by Miss Barbara Kasky, now Mrs. Ernie Hamanaka, and Professor Jack Gugatas on a substance called beta-cornorsterone. And you will observe in this three-dimensional or the two-dimensional representation of this X-ray structure determination 6 blue dots, 1, 2, 3, 4, 5, 6. My favorite color is not red. Now, those 6 blue dots represent asymmetric carbon atoms or chiral centers, and indeed, in this molecule of cornosterone, they represent the 6 contiguous asymmetric centers in the AD portion of the vitamin B12 molecule. And so now, if we may have the next slide, we see shown in a two-dimensional and perhaps more easily recognizable form, beta-cornosterone. Now, you see, it is a tetracyclic substance, a 6-membered, 5-membered, 6-membered, 5-membered ring. The name is mildly amusing, or at least I meant it to be so. The core was hopeful. We were hoping that this was going to be an important intermediate in the preparation of some corins. The norsterone refers to the fact that this tetracyclic nucleus is that of a norsteroid, if, of course, we ignore for the moment the presence in the skeleton of 2 nitrogen atoms, one here and one here. And then finally, if you pronounce this name in Slovene, it comes out to be something like cornerstone, which is what we hoped it would be. Well, now, beta-cornosterone was prepared by a sequence of some 32 steps or so. What you count as a step in synthetic operations of this sort is rather difficult to define. There are certainly more than 32 transition states involved. But in any event, through a fairly long but very efficient sequence, this beta-cornosterone was prepared, and it does contain the 6 contiguous asymmetric centers in rings A and D of the vitamin B12 molecule. There they are. 1, this is ring A, 1, 2, 3, 4, 5, 6. And they are all oriented relative to one another in precisely the way that they are in the vitamin B12 molecule. Now, the dotted arrow here represents a hypothetical transformation in which this 6-membered lactam ring is cleaved by methanol. And over here, then we've swung, this is not a chemical change, but just a geometrical movement. We've swung that bottom ring round over to this. There's the methanol, the hydrogen, and the methoxyl. And there now you see rings A and D. And on the right, this representation of this open form, hypothetical open form of cornosterone shows more clearly, I think, that this is a substance which might very well serve for the introduction into a more complicated molecule of the AD portion of the cornosterone, of the vitamin B12 molecule. And as I said, I'm going to start with cornosterone, not because I really wouldn't like to tell the whole story up to cornosterone, but because there simply wouldn't be time to do it. And the work leading to cornosterone is fairly well described in these earlier publications, which represent lectures which I or Professor Eschenmoser gave from time to time during the course of the work. I would mention that it was in the course of the sequence of steps leading to cornosterone that the phenomena were observed which led directly to the principle of orbital symmetry conservation. And this, I think, is perhaps the most dramatic case of the influence of work on natural products on general chemical principles. Now, I said that the representation or the relationship between these two structures shown here is hypothetical. That lactam ring cannot simply be opened by methanol to give this product. It's much too stable a lactam ring, and a product of this kind would immediately re-lactamize. However, a very closely related change can in fact be carried out, and that is shown on the next slide. Now there again on the left you see conorsterone, and what I've shown here at the top is the result of the treatment of conorsterone with methanolic hydrogen chloride. And the lactam ring is indeed cleaved in the way which I showed as a hypothetical process before. The difference here is that the resulting beta-amino, alpha-beta unsaturated carbonyl system does not survive, but rather is transformed into this new system, this system which is methylated on oxygen, you see, a methoxy unsaturated imine system. There is no free hydrogen on this nitrogen, and that effectively blocks the relactamization. And so if you just turn again, carry out this non-chemical but just spatial operation, the product of this action of methanolic hydrogen chloride on beta-conorsterone is hesperamine, which is a stable open substance showing the AD with the 6 asymmetric carbon atoms. And furthermore, I might take this opportunity to point out that hesperamine has chains attached at various places to ring A, for example, which are very reminiscent of those in vitamin B12 itself. These two methyl groups, for example, here attached to ring A, are present in the ring A, and we have an acetic chain and a propionic chain. Now, as far as ring D is concerned, the opening of the lactam ring of conorsterone gave us one more acetic acid chain, and then, of course, we have this ring which clearly permits, or at least allows one to think of, a cleavage of this carbon-carbon double bond to give another propionic chain. And of course, ring D in vitamin B12 does bear a methyl group at this position, an acetic chain, and a propionic chain. Now, as such, however, and this was a very important point, hesperamine was not particularly promising intermediate for vitamin B12 synthesis. And you can see in an instant why. Namely, I've directed attention to these various chains. It is true that the substance hesperamine can be converted by ozonization with cleavage of this carbon-carbon double bond to an aldehydo ester of this structure. But now notice the dilemma which is created thereby. That is that we have a carbomethoxyl group here, 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 and here. And you may remember now, if you think back to the structure I showed you originally for vitamin B12 itself and for our immediate objective, cobyric acid, this chain attached to ring D must in some way be differentiated from the other chains. This is the chain, this is the point, this is the terminus at which that isopropanolamine ribose phosphate ribose chain.